Hello and welcome to Physics Teacher. In this tutorial, I'm going to go over the titration calculations for weak acids and weak bases as we see in the grade 12 chemistry course. So let's start with this example. So here we have acetic acid. This is a very weak acid and we have 25 milliliters of it in our flask. We have an unknown concentration, so we're going to need to figure out that concentration, and then we're also going to calculate the pH and percent ionization of that acetic acid sample. Now we do a titration, and to titrate this weak acid, we're going to use a strong base, in this case sodium hydroxide, with a concentration of 1 moles per liter. And we end up titrating 27 milliliters to get to that equivalence point. So let's start with the equation for the titration. So we have sodium hydroxide. And then we have our acetic acid. And that's going to give us some water. So this is just a neutralization reaction. And a salt. So we have sodium acetate. Now this salt is interesting because it's going to dissociate in water and produce hydroxide ions. So we're going to reach our equivalence point for this case at around pH of 9. And that's why for this example, it's great to use phenolphthalein as our indicator because it'll change color around that pH of 9. And that is when we have reached our stoichiometric equivalence, or the end point for our titration. So let's look at what we know. So for sodium hydroxide, we have a concentration of 1 mole per liter. And then we also have our volume, which is right here. We're going to change that into liters though. So divide by 1,000, 0.027 liters. And then we can figure out the number of moles. So we're going to use our equation, our concentration equation, which is moles per volume, but rearranging, moles is concentration times volume. So when we do our concentration times our volume, we get the number of moles as 0.027 moles. Now, since we have a 1-to-1 ratio in our equation, we know that the number of moles of acetic acid is also going to be 0.027 moles. And since we know our volume of acetic acid, change that into liters. So divide by 1,000, 0.025 liters. We can use our equation, which is concentration is moles per volume, to figure out the concentration of acetic acid, which turns out to be 1.08 moles per liter. All right, so we have the concentration of acetic acid, but I also want to know the pH and percent ionization. So let's now look at what's going on in here. So in our original sample, we have acetic acid, so CH3COOH, colliding with water molecules. And now this does not go to completion because it's a weak acid, so it's going to be in equilibrium. Right, so we're going to take one of these hydrogens and give it to water, so we're going to have hydronium plus our acetate. And now from here we can write our equilibrium law. So we have our constant, our acid constant, is equal to the concentrations of the product of the products. So we have hydronium and acetate divided by our reactants, which is our acetic acid. We can also look up what the equilibrium constant is for acetic acid, which turns out to be 1.8 times 10 to the negative 5. Now we can do our little ice chart if you like. You can go on the side here, I, C, E. And we'll have 1, 2, and 3, just because I am lazy. So 1, 2, and 3. So our initial concentration we have as 1.08, and initially nothing. And then we're going to have some change. Now it's all a 1-to-1 ratio, so these are going to change by a certain amount x, and this is going to decrease by that amount x. So our equilibrium concentrations is 1.08 minus x, and for hydronium and acetate, it's just x. I don't really need the plus. Okay, so that means we have x and x, which gives us x squared, divided by 1.08 minus x. Now, we can actually drop that x, because if you take the concentration, the initial concentration of our acid, and divide that by the constant, or the acid constant, if that number is greater than 100, which it definitely is, we are safe to drop this x. It's not going to make much of a difference. So that makes this easier to solve. And we can just cross multiply and take the square root, and we can get x to be the square root of, we have our constant, 1.8 times 10 to the minus 5 times by 1.08, and we get x to be 4.41 times 10 to the minus 3 moles per liter. So that is actually our concentration of our hydronium. So since we know the concentration of hydronium, what we can do, and I'm going to do this somewhere else, don't know where, I'll do it over here. So we can figure out the pH, right, which is minus the log of our concentration of hydronium. Now that we know what that is, we can substitute that concentration into our equation, and we get the pH to be 2.4. All right, one more thing to do, and that's to figure out the percent ionization. So the percent ionization, I will do that up over here. It's all over the place here. So percent ionization, that's going to equal to how much hydronium ions we have. Divide that by our concentration for the molecular acid. So in this case, acetic acid, and then multiply by 100%. So here we have, so hydronium, 4.41 times 10 to the minus 3 moles per liter, divided by the original concentration of our acid, which was 1.08, and times 100%, and we get a percent ionization of 0.41%. And that is our titration of a weak acid with a strong base. Moving on to our second example, this is the opposite example. In this case, we're going to titrate a weak base with a strong acid. So in this example, our weak base is going to be ammonia, and we have 25 milliliters of it. We're going to titrate it with our strong acid, hydrochloric acid, at a concentration of 0.5 moles per liter. And we end up titrating 18 milliliters until we reach our equivalence point. Same as before, calculate the pH and percent ionization of, I forgot to change this. Not acetic acid, but ammonia sample. Ammonia sample, which is our weak base. All right, so let's get started. Just as before, we're going to write our titration equation. So we have ammonia plus hydrochloric acid, and that's going to give us ammonium chloride. So let's go ahead and write what we know. Just as before, a hydrochloric acid, we know the concentration is 0.5 moles per liter. We know the volume, let's change it into liters, so 0.018 liters. And we can figure out the number of moles by doing concentration times volume. And when we do that, we get 9 times 10 to the minus 3 moles. All right, and just as before, since this is a 1-to-1 ratio, we now also know the moles of ammonia. It is 9 times 10 to the minus 3 moles. Just some simple grade 11 stoichiometry there. All right, and we know the volume is 25 milliliters. We'll change that into liters, so 0.025 liters. And we can get the concentration then by doing moles per volume. And when we throw that onto our calculators, we get 0.36 moles per liter. All right, so great. We know the concentration of ammonia. Now this will actually dissociate to produce ammonium ions, and then that is going to produce hydronium ions, which is going to create a slightly acidic solution at around a pH of maybe 5. And so, which in this case, we use methyl orange because that will change color at around that pH. So that is how we determined our endpoint. But now that we know the concentration of ammonia, we can calculate its pH and percent ionization. So let's see what was happening in that original weak base solution. So we had ammonia ions colliding with water. And in this case, one of these hydrogens from water is going to ammonia. Now, this does not go to completion. It's a weak base, so it's an equilibrium. And we end up with ammonium plus hydroxide. Okay, so that hydroxide concentration is what we want to go for. Okay, if we want to figure out the pH. So let's start by writing our equilibrium law. So we're going to have NH4 and hydroxide ions all over our ammonia ions. Now you can look at what your base constant is, and it turns out to be 1.8 times 10 to the negative 5. No, that's not a mistake. It's the same as the acid constant for acetic acid. And now what are our concentrations, our equilibrium concentrations? Let's make our ice chart to figure out what those will be. So initial, change, and equilibrium. And we'll do 1, 2, 3 because I am lazy. So our initial concentration of ammonia, we figured out what that is. It's 0.36. And we don't have an initial concentration here. But then there's going to be a change. This is all a nice 1-to-1 ratios. So what these two gain, whatever that is, X, this will lose. So our equilibrium concentrations for ammonia is 0.36 minus X. And then ammonium and hydroxide will be X. So filling out this equation, we have X times X, which is X squared, all divided by 0.36 minus X. And once again, because our initial concentration of our weak base divided by that constant is much, much greater than 100, we are free to cancel out this X. It won't really make a difference. So solving for X, again, cross multiply, take the square root. X is going to be the square root of 1.8 times 10 to the minus 5 times 0.36, which gives us 2.55 times 10 to the minus 3 moles per liter. Okay, now let's figure out what the pH is. Now we don't know what the concentration of hydronium is. So what we're going to do first is we are going to figure out what the pOH is. So I'm going to do that over here. pOH. is minus the log of the concentration of hydroxide ions. And we know what that is. It's right here. We just solved for it, right? X is the concentration of hydroxide ions right there. So if we plug in that value into our calculators, we get pOH of 2.6. Now, since we know that pH plus pOH will equal 14, pH will just be 14 minus 2.6, which is 11.4. So we figured out what the pH of that original ammonia solution. Lastly, we need to figure out what that percent ionization was. So I'm just going to squeeze that in here. So the percent ionization is equal to our concentrations of hydroxide ions divided by the original or initial concentration of ammonia times 100%. So we have 2.55 times 10 to the minus 3 divided by 0.36 times 100%, and we get our percent ionization to be 0.71%. Well, I hope this helped, and if you're doing a titration with either a weak acid or a weak base, you can follow these same steps. Good luck.